Or formally, when you do mathematical theory, there's also a combination of both things, which is termed a Poincare section. So maybe I can briefly sketch what is a Poincare section. Let's again suppose we have a system which evolves in 3 relevant dimensions. So maybe this is somehow the path of the system. And the Poincare section is now that we take a lower dimensional manifold, let's say some plane in this 3-dimensional space, and we just consider the points of time and the points in space where the trajectory hits this plane. Yes, so that's the idea. Either we take both or we take only in one direction. And this is called a Poincare section. Okay, what we would like to know first is when we have one single time series, or maybe let's say a low number of time series, what might be the actual dimension of the state space in which your system works. Okay, for example, for the climate, I already told you that there is usually a very high dimension. We can think about numbers in the order of thousands, 10,000s, or even more dimensions. So how can we get an estimate of this? And the idea is to apply this method of singular spectrum analysis. I've already talked before in my last lecture about the application of the singular spectrum analysis in terms of detecting periodic components, but we can also apply this in a slightly different sense by means of looking when we do this decomposition of an embedded time series into different components, how many of these components are actually relevant. And if we know this, we know or we have an estimate of how many relevant dimensions contribute to our phase space. So that's the idea of this so-called embedding theorem of Tarkins. So what we can do is embed our time series to a higher dimensional object by just considering different values of our observations made at different times, combine them into one vector, and for a good choice of the dimension of this vector and of the delay between the different observations, this might give us a reasonable approximation of the high dimensional invariant dynamics of our system. If this dynamics is deterministic, that's the important point. If we have a stochastic system, it won't work. Yeah, we have to suppose that our system is deterministic in this case. So, okay, the embedding dimension, this M, can be estimated from the singular system analysis as the number of significant components. And this is also called the concept of attractor reconstruction. And I give you only some example which you might maybe better consider as a counter-example. So it was quite fashionable in the 80s to dispute whether or not there is a low-dimensional attractor for the climate system. So, which means, can we describe the main dynamics of the climate by means of a very low-dimensional system? So in this case, maybe a 2-dimensional one. And there's, for example, this paper of Nicolis and Nicolis, who took some of these paleoclimate records. We already had one of them, so this is another one. This is now from a sediment record. And what is measured is the so-called delta 18O. It's again some isotope ratio, which gives you some idea of temperature variability. So that's all you should have in mind. And what they did was trying to get some reasonable embedding into 2 dimension of this time series. And they concluded that this object might be a signature of some low-dimensional chaotic object which controls the dynamics hidden in this time series. So there was a lot of dispute after this paper there were, let's say, 10 or 15 papers discussing whether or not this result is meaningful. So in fact, I think at the end it came out that it cannot be true for some methodological reasons, but at least it should illustrate how this idea of attractor reconstruction and embedding works in principle. Maybe to give you once again another example on the application of the singular system analysis. You have again already seen this time series of the Southern Oscillation Index. So it's an index which quantifies pressure variability in the Southern Pacific Ocean, and it's also related to the El Niño phenomenon. And what you see here from this plot is when you do this embedding, very high dimensional embedding, and compute, perform the singular system analysis, you end up with exactly 5 components which are much more significant than the rest. So these 5 would be a reasonable number for the dimension of your phase space. So that's the idea how this method works in principle. Okay, is this clear so far? So this is, if there's no question, this is one specific concept of dimension analysis. Note that in these terms, dimension is understood as topological dimension of a phase space. So how many variables do I need to describe my system properly? There's also another concept called dimensions, which works kind of different. And that's the concept of fractal dimensions. Fractal dimensions you can consider as follows. When you have a complex deterministic system, such a system is usually characterized by certain redundancies between the individual variables. These redundancies come into the system due to the nonlinear interactions. So you have different variables. These different variables do interact with each other, are coupled with each other by some certain nonlinear functions. And due to these nonlinear interactions, we have redundancies in the system. So which means we would actually only need to observe a lower number of variables instead of the full system. And the second point is something I addressed already this morning. When we have a system which, particular systems which obey long-term persistence, so long-term memory, the values of our variables are determined by values of the same variable in the past, which can go back a considerable amount of time. This leads to a certain scaling or self-similarity in the different statistical properties. And this scaling also contributes to these redundancies in a certain way that one can, from a geometric point of view, say that the actual dimension of the phase space, so the actual dimension, these objects on which the dynamics occurs in our phase space, are not integer. So that's a bit tricky or a bit weird maybe notation, that dimensions must not necessarily be integer, they can also be fractal. So it's actually a transfer of this notion from discrete mathematics in terms of fractal sets to time series analysis. Just to give you one idea how this concept of fractal dimension works, I will illustrate this by the maybe most simple approach, the so-called capacity or box counting dimension. The idea is you have some geometric object. It can be such a time series in phase space. It can be any specific set in a mathematical sense. And we want to try to cover this set by boxes.